In this presentation, I'll be explaining three-phase fully controlled bridge rectifiers. Now coming to a three-phase fully controlled bridge rectifier with RLE load or full converter or 6-pulse converter we call. In per cycle, there will be 6 pulses, that's called 6-pulse converter, or also called full converter, three-phase fully converter. Design that we are considering is in a continuous conduction mode. The current is continuous through the load. We are continuing a continuous conduction mode. Therefore, this is the circuit topology for a three-phase fully controlled bridge rectifier in which three-phase supply is given here. There are 6 thyristors, 6 switches, thyristor switches are there. That is normally it is marked as T1, T3, T5, T2, T4, T6. Why it is marked like that one? The firing sequence like this one: T1, T2, T3, T4, T5, T6, T1, T2, like that one. In order to to make the firing sequence in that order, we are numbering this one: T1, T3, T5, T2, T4, T6. And this is odd group. This one is no, that each thyristors conduct, out of this one, each thyristor will be conducting for 120 degree. Now we'll see that one. Let's say three-phase supply here, phase A, then phase B, that's 120 degree apart, shifted from phase A, and again phase C. These are called the phase voltages. The voltage of each phase with respect to the neutral is called the phase voltages. That is VA, sometimes we call VAN, VBN, VCN. Now it is written as VA, VB, VC, same thing. Therefore, these are the phase voltages of these three at the input of this one. And here, 6 thyristors are divided. In this one, these 6 thyristors are there. In that is divided into two groups as such. This is called, we call it as positive group, and this is called negative group. Positive group means that these switches conducts when during the positive half cycle, because in that instance this are getting forward biased. When this is positive, this is getting forward biased. Similarly, that is why they are called positive group. So the six thyristors are divided into two groups. And upper group, that is T1, T3, T5, they are called positive group. That is because during the positive half cycle, that can be triggered as such. Similarly, then during the negative half cycle, these are getting forward bias. That is T2, T4, T6. These are getting forward bias because this is a negative cathode, and that is getting that is getting forward bias. Of course, negative cycle, that is these are getting forward bias. That is why they are called lower group, or that's called the negative group. During the negative half cycle, these are getting forward bias. The lower group T2, T4, T6 are getting forward bias. That is why they are called the negative group. And this is RLE load here. And here you can say that T1, it is opposite here, is equal to T4, that is marked here, T1, T4, and similarly T3, T6, and here T2, T5, like that one. It is marked like this one, that is symbolically it is there. And if you want one more thing I want to convey is here, these are the phase voltages are, we are marking it as VAN, VBN, and VCN. That is written as same thing, VA, VB, VC here. And in order to calculate the line voltages, the correspondingly, you know that this, for example, this is equal to, say, this is VAN and this is VBN. VAB can be calculated as VAN minus VBN. For VAN, this is producing to in this direction, then this is equal to VAB. So this is the line voltages, VAB, like that we can get here, this is equal to VBC and this is equal to VCA. That is here, this is equal to, therefore this is equal to VCA, like that. These are the line voltages that derived from the vectorially adding its corresponding phase and opposite to that VAN and minus VBN, VAB, like that one. One thing is that you can see that one from the phase voltages, line voltage is shifted by 30 degree. Line voltage is shifted by this VAN by 30 degree. And then one more thing is that the magnitude of this one is equal to √3 times phase voltage. For the line voltage, that's why we can draw the line voltages. This is a line voltage diagram as such. VAB, of course, VAB, VCA, okay, VAB, VCA, and VBC, like that. This line voltages can be drawn here. That is drawn at the below here. These are the line voltage that is obtaining by this mechanism. Of course, its magnitude is √3 times the phase voltage, and there's a phase shift is there. But these are the line voltages, and these are the phase voltages. Now to explain the switching operation here, what we are considering here each thyristor is conducting for 120 degree. Each thyristor is conducting for example. Now, if you are triggering this T1 for a certain angle alpha here, T1 at this instant, if you firing up the alpha, that is T1 is conducting. T1 is conducting. The same time, already the T6 is also conducting from the negative group, because here you can say that T6 is also conducting. Therefore, T1 and T6 are conducting at this firing angle, at a firing angle alpha here. Therefore, when T1 and T6 are conducting, T1 means that phase A is coming here, and T6 is coming. T6 is T2, T4, T6 is this one. The phase B is coming here. Therefore, this voltage become now VAB. That is, here you can say that this the voltage across the load will become the line voltage VAB. Now, see here, from here it comes in VAB. After this one, here VAB, and at this instant here the lower one is, that is from until this one T6 is conducting, but here again T2 is fired here. Now T2 is fired at this instant. For when T2 is firing here, now this will become the C phase, and this will become the again the same as the A phase, because T1 and T2 are conducting. When T1 and T2 are conducting, this is the phase A and this is the phase C. Therefore, this voltage equal to VAC. That is why from here it is equal to VAC. Like that one, depending upon the thyristor that is conducting from the positive group and negative group, you can plot what is the voltage that is coming across this RLE load. That is the only the line voltage. At that instant, what is the line voltage that will be available here? Therefore, that is a way in which you can plot the voltage across the RLE load for different instance of the firing. Therefore, these are the thyristors. These are conducting for different duration. Like here, for different, you can trigger like that one. T1, of course, T1, T3, T5. Here, T6, T2, T4, T2, T4, T6, like that. Or here, the firing sequence will become T1, T2, T3, T4, T6. Like in that sequence, you can fire that one. Each one for a 60-degree interval that can be fired. Therefore, this is the phase voltages at the input side, and the output side, this is the the voltage that is available across the load. As I explained in the previous slide, three-phase fully controlled bridge rectifier. It's a bridge rectifier. This is a bridge T1, T3, T5, T2, T4, T6. Like the three leg. In each leg there are two switches. Three-phase supply is given. The voltage across the load, RLE load, will be depending upon one from the positive group and one from the negative group will be conducting. Which one is, that depends upon the instant at which. Here you can see that one. We'll see that for T1 will be conducting from alpha plus 30 to alpha plus 30 plus 120. That is, here this is a 30 degree. The firing angle is that from alpha to 30. That is from the instant this alpha plus 30 to T1 will be conducting from alpha plus 30 plus 120. The alpha plus 30 to alpha plus 30 plus 120. Each one conducts for 120 degree. For like that one, different thyristors, that duration conduction can be written as for T2 alpha plus 90 degree to alpha plus 90 plus 120 degree. Therefore, each device conducts for 120 degree duration. Like that, from the lower side also you can write it as, that is, what is from the lower side also we can write it as, T2 is conducting from alpha plus 90, that is from alpha plus 90 plus alpha plus 90 plus 120. Similarly, next T3 will be conducting from alpha plus 120 to alpha plus 120 plus alpha plus 120 plus alpha plus 150 plus 120, alpha plus 150 plus alpha plus 150 plus 120. Like that, you can mark which are the devices that are conducting depending upon the firing angle, and from this one you can find out at any instant. This is a way in which how you can draw the voltages. At any instant, you see what is the thyristor from the positive group and what is the thyristor from the negative groups are conducting. Depending upon that one, that corresponding phase will be connected here. For example, if T1 and T2 are conducting, this point is connected to the phase A and this point is connected to phase C, so that this voltage will become VAC. Now, if this is connected some other phase, like if it is equal to say T1 and if it is equal to T6 here, that is, this will be connected to the phase A and this will be connected to phase B, or here the voltage will become VAB. That is what shown here, VAB and VAC, like that one. Therefore, depending upon the thyristors that are conducting from the positive group and negative group, the voltage that will be changing. Therefore, what is marked here, that is the voltage that is available across RLE load. Therefore, this whatever shown is the line voltage. This is the phase voltage, and these are the different instant of conduction of these thyristors. This is the positive group of thyristors T1, T3, T5, like that one. This is the negative group like T2, T4, T6, and the firing sequence, as I already told you, T1, then after 60 degree T2, then T3, T4, T5, T6, again T1. The firing sequence is like that one. In order to make that one only, this is numbered like this one: T1, T3, T5, T2, T4, T6. Now again, for a firing angle of alpha equal to 30 in each duration, it as follows. If alpha is equal to, say, from this alpha equal to 30 degree, here this alpha equal to 30 degree, for this instant equal to 30 plus 30, 60 comes here. For 0 to 0. For 0 to 60 degree, you can say that from 0 to 60 degree, what all the devices they are conducting. Here, 0 to 60 degree, here only the T1 is conducting, or until that one, T5 and T6 are conducting. When T5 and T6 are conducting, from this one, you can see that one, from if the T5 and T6 are conducting, here C phase and here B phase, so VCB comes here. That is why it is voltage equal to VCB here. Again, from this point, that is from 60 to 120, you can see that T1 and T6 are conducting. T1 and T6 are conducting, and T1 and T6 are conducting here. T1 is conducting, then the phase is equal to A here, and T6 is conducting, the phase is equal to B, then is voltage equal to VAB. Therefore, that voltage is equal to VAB, output voltage equal to VAB. Then again, it is equal to from 120 to 180. From 120 to 180, we can see that T1 and T2 are conducting. T1 and T2 is fired, T1 and T2 are conducting. When T1 is conducting, phase A here comes here, and T2 is conducting here, it is equal to phase C is conducting. Therefore, VAC comes here. That is why voltage is equal to VAC. Like that one, depending upon the thyristor from the positive group and negative group conducts, there you can see that corresponding voltage, that line voltage will be available here. That voltage will be available, so that you can see that this is a, say, having a ripple voltage like this one. Say I say rectified voltage here. In here, per one cycle here, if you see that this is a line frequency, of the frequency time period as such, in each one there will be 6 pulses will be available. That is why it's called 6 pulse converter. For different duration, what are the devices conducting from the positive group and negative group, and what is the voltage across the load, RLE load, what is the line voltages that is marked here, that is written here. Therefore, as I explained the previous slide here, when T5 and T6 are conducting, that is until this one, the voltage equal to VCB. When here T6 and T1 conducts, the voltage equal to VAB. When T1 and T2 are conducting, the voltage equal to VAC. Like that, depending upon the thyristor from the positive group, only 2 thyristors will be conducted at any instant. One film from the positive group and one from the negative group. Depending upon which thyristor can be triggered, that voltage, the line voltage will be available here. And that is the way in which we can plot the load voltage depending upon the thyristor that is conducting from the positive group and one from the negative group. Now let us derive the average DC voltage across this RLE load for a certain firing angle. As we have seen, this is the firing angle as such. This is fired as such. At this instant is fired, and these are the different voltages that is coming across the RLE load, as we have explained in the previous slide. So this is the voltage, and we have to find out what is the average voltage here. What's this average value of this voltage to be found out. Mainly, this is here. There are in per cycle. If you see the per one cycle here, per cycle there are 6 pulses are there. That is called 6 pulse converter. In order to calculate that one, what we are doing is that we are calculating what is this area 1, then you are multiplying by 6, and that is divided by for a 2 pi radians. Therefore, 6 by 2 pi integral, here it is equal to alpha plus, this is a 30 degree, alpha plus 30, and here until that this is equal to alpha plus 30 plus 60, or alpha plus 90, alpha plus 90. Therefore, that voltage, line voltage is coming here. This is the line voltage, which is equal to root 3 times phase voltage. Root 3 Vm, I told you, there's a phase shift of 30 degrees there for the line voltage. That is why plus 30 comes here. Sine omega t plus 30 root 3 Vm. Therefore, we are integrating this one. Then you will be getting the, that is what is the, of course, the area under one pulse, that is spikes, is calculated. Then such there are 6 pulses are there. per time period, or that per one frequency here, and that is spread over to 2 pi radians. For 6 by 2 pi integral that one, we'll be getting 6 root 3 Vm divided by 2 pi cos alpha plus 6. This is equal to root 3 taken outside, Vm is outside, 2 pi here, sin omega t plus 30. That can be, written as, therefore, the integrating here, sin omega t plus 30, it will become, okay, minus cos omega t plus 30, and minus omega, and here we have to change the limits as it, because minus cos omega t plus 30, you can do that, cos omega t plus 30, and that range can be, the limits can be changed, like here alpha plus, that is alpha plus 30 can be here, and alpha plus 90 can be here. Therefore, substituting that one, we will be getting, it is equal to cos alpha plus 90, no, that is, 90, 90 minus 30, of course, alpha plus 60 minus cos alpha plus 120. Anyway, you can reduce that one here, and we'll be getting, it is equal to cos 60 can be 90 minus 30, and cos 120 can be 90 plus 30. Therefore, substituting here, cos A minus B minus cos A plus B, like that one, 2 sin A sin B, like 2 into sin alpha plus 90 sin 30, like that one. Substituting that one here, it is equal to 6 root 3 Vm divided by 2 pi into 2 cos alpha into sin 30, that is equal to half, or half cancels, or it is equal to 2 pi or 3 root 3 Vm by pi into cos alpha. 3 root 3 Vm by pi into cos alpha. Actually, root 3 Vm equal to the maximum value of the line voltage, because Vm is the maximum value of the phase voltage. Root 3 Vm is the maximum value of the line voltage. One more equation is, you can write it as, it is equal to 3 Vml by pi cos alpha, or it is equal to 3 root 3 Vm by pi cos alpha. Now, in this case, we can say that one, if alpha equal to less than 90 degree, this will be positive, or that will be working as a rectifier. Now, if alpha is more than 90, this will become negative, or it can work in an inversion mode. Therefore, if alpha is less than 90, the average output voltage is positive. That is rectification process, this one. When alpha is less than 90, this will be working as a rectifier. And if alpha is more than 90, provided you are connecting an active, DC source like DC motor, etc., that in that case, the power can be fed back into the source. That is called the inversion mode of operation, provided you are working this one in a more than 90 degree. Therefore, it can be worked as a rectification mode or inversion mode. If alpha is less than 90 degree, it will be working as a rectifier mode. And if alpha is more than 90, that will be working in the inversion mode. Therefore, the equation for this average DC voltage is equal to 3 root 3 Vm by pi into cos alpha, or 3 Vml by pi cos alpha. Now, in three-phase fully controlled bridge circuit, what we already discussed here is a continuous conduction case. In which continuous conduction case, the load current is assumed to be constant. Therefore, the current through this RLE load, that is, we are assuming constant. It's RLE load constant. It's a continuous conduction one, and depending upon the which thyristor is getting more forward bias, here positive group and this is a negative group, either one from the positive group and one from the negative group will be conducting. Depending upon the which thyristor, will be getting the corresponding line voltage that will be available across that one, this one. So that is the way in which it is rectified. The three-phase AC is rectified into a unidirectional voltage VDC, and the corresponding equation we derived, it is equal to 3 Vml pi, 3 root 3 Vm by pi cos alpha, or 3 Vml by pi cos alpha. This is the average voltage available across the RLE load. And here the different durations, different thyristors also we have explained that one. Here we can see that one. Here T1 is conducting, T3 is conducting, T5 is, T1, T3, T5, like that, that is repeating like that one. And similarly here T6 is conducting, T2 is conducting, T4 is conducting, like that one. Therefore, these are the different thyristors from the positive group, and the negative groups are conducting for different instance. Now, if we have drawn this voltage that is coming across the load, depending upon these thyristors that are conducting. And one more thing I want to explain is that input current. If you see the input current here, you see that one. For example, the phase A input current, if T1 is conducting, that will be positive. The current will be in this direction. Now, if T4, the other one, negative group thyristor is conducting here, you can see that current is opposite. I4 will be opposite. Therefore, if you plot that one, when T1 is conducting, you are getting the same as this corresponding current I0. That is why here when T1, if you just plot that T1, as T1 conducts, you will be getting plus I naught. And when T1 is not conducting, when other resistors are conducting, we can see that one, either T1 or T4, they are not conducting, the current through this line equal to 0. That is why you will getting a 0 current. Then again, when T4 is conducting, that is from this duration, you can see that T4. Here the T4 is conducting. As T4 conducts here, the current is opposite direction here. That is why you are getting a negative current the source side. But the source side current is like this one. This is the load current. A constant current is flowing through RLE load. But input side per phase IA, that is like this one. From, in this case, from 30 plus alpha, that is until 150 plus alpha, that is plus I naught, and then it is 0, then again it is equal to minus I naught. Therefore, this is the shape of the curve at the, or the waveform at the input of the source current phase A when a constant load current is flowing. Now we are going to analyze what are the different harmonics in the source current in this case for different firing angles. Therefore, this is the firing angle like alpha. This is why it is 30 plus alpha here, and until 150 plus alpha, it is plus I. Then this duration, again this is equal to 60-degree duration, it is equal to 0. And again for 120-degree duration, it is equal to minus I naught. Therefore, this is the line current of the phase A corresponding to alpha equal to 30. This is shown for alpha equal to 30. As I told you, the DC voltage, average DC voltage we are derived, it is equal to 3 root 3 Vm by pi cos alpha. If alpha is less than 90, this quantity will be positive. That is called the rectification process or rectifier. The AC voltage will be converted into a DC voltage. That's called this is working as a rectifier. Now, if the firing angle is more than 90, here, if the firing angle is more than 90, of course, this is equal to a negative quantity. In that case, if you are an active source is just like a RLE load in the case of a DC motor back EMF, it's an active source here. In that case, this one, if it is operated at a firing angle more than 90 degree, the power will be flowing from the load into the source, or this converter will be working as an inverter, provided you are connecting an active load. Therefore, this is a rectification. This is the inversion process when alpha is more than pi by 2. When alpha is less than pi by 2, it's called a rectification operation. Now, if alpha equal to 90 degree, we can see that as per this equation, it is equal to 0. Vm 3 root 3 Vm by pi cos 90, which is equal to 0. That is why for 90 degree, you can see this one. See, what is that one? If you take the average of this one, that is equal to 0. Average voltage, if you take the average of this darkened waveform, that is equal to 0 for a 90 degree. Now, if alpha is more than 90 degree, for example, it is 120 degree, this is the waveform as such. Here, again, you can plot based upon the thyristors that are conducting. The corresponding voltage waveform is like this one. And here you can say if you take an average of this one, you'll be getting a negative voltage here. Therefore, if the firing angle is more than 90 degree, then the polarity of the voltage here as per this one is negative. Or we can say that one, if this is working in more than 90 degree, if it is an active load, the power will be flowing from the load side into the source side, or this converter will be working as an inverter, power flow in the reverse direction. Therefore, that is possible only if the firing angle is more than 90 degree. Therefore, average output is negative and the power flow can be in the reverse. Therefore, if alpha equal to 120 degree, this is the output waveform. And if you take the average voltage of this one, that will become negative. Therefore, alpha equal to 90 degree, output voltage equal to 0. When alpha equal to 120 degree, you will be getting a negative output voltage. Therefore, three-phase control bridge will be working as a line commuted inverter. That is, the power will be flowing from the load into the source, if provided you are providing a active load, active source as such, active source like a back EMF of a DC motor like. But of course, here the polarity is to be reversed. The polarity is to be reversed in this case. In order to, when it is working as an inverter, the polarity is to be reversed here. Therefore, if the firing angle of this, thyristors are kept more than 90 degree firing angle and induced EMF reverses, the polarity of this voltage is now here negative with respect to this point. Therefore, induced voltage polarity reverse, because as per this one, if alpha is more than 90, this will become negative. For here minus and here plus. and during the inversion the average output voltage is negative, but the average output current is positive. But current is always like this one, and here the voltage is polarity is reverse. Of course, you can say the power is negative. If you calculate the power, it will become negative. That means that negative power means that the power is not dissipating, it is supplying as, or the power is flowing from the load side into the source side, or the converter is working as an inverter, that is in this region. When pi by more than pi by 2, it is working as an inverter. In the inversion mode, it is working. That it is called the line commutator inverter. Why it is the line commutator? Means that it is the device is or gets commutated by the line voltage itself, because in order to turn off an SCR, you know that the current through the SCR should go below the holding current. Therefore, that mechanism is taking place because of the reverse voltage, that is when you are triggering, for example, when T1, first T1, assume that T1 and T2 are triggered. I mean, that's they are conducting. T1 and T2 are conducting. At that instant, after say, I mean, after 60 degree, what we are that is T1 and T2 are conducting. Next, we will be triggering on T3. Therefore, T3 will be the incoming SCR and T1 will be the outgoing SCR. Therefore, as we are triggering the T3 here, that voltage comes here, that will be automatically turned off. Therefore, say natural commutation or line commutation happens, and the device which is already in conduction, that's called outgoing SCR, that gets turned off, and the incoming SCR that starts conduction. That repeats. Therefore, that's the way in which the SCR which is already in conduction gets turned off. That is line commutation. There is no forced commutation. Naturally, when as the voltage across this one goes, I mean zero, the corresponding current goes less than the holding current, and the device gets turned off. That's called the line commutator inverter. And here this is operated more than 90 degree, and here the polarity is to be reversed, and the power will be flowing from the load side into the source side. That is the mechanism normally doing in the even regenerative braking, also doing the same mechanism. In the next presentation, I'll be explaining, or I'll be going through the analysis of this 3-phase full converter or 6-pulse converter.